Welcome to the lectures on modern digital communication techniques. Till the previous lecture, we have been looking into source coding, and what we have seen is fixed length coding, where we have assigned a fixed number of binary strings for a particular symbol. And of course, we do not need to mention we are looking at discrete sources. So, for discrete sources, what we mean is that we are having a source which has an alphabet. Alphabet would mean a group of symbols which is fixed for that, and then the source produces each letter or each symbol of that alphabet at a time, and there is a certain probability for each of these symbols. So, when we do fixed length coding, what we said is we assign a fixed number of bits for each symbol, and we do it in such a way that each symbol gets a unique code. That means there is no two symbols which are assigned the same code. So, every one of them are different. Now, when we did this, we saw that there is a gap of approximately 1 bit that can happen, and compared to what can be done in a better way. So, we did another method where we saw that instead of taking one symbol at a time, if the source outputs are grouped or if they are buffered, and we take n number of symbols. So, if we assume that there are m symbols in the alphabet, and now we say that we take n symbols and make a new symbol out of this, which is a super symbol. So, then we can reduce the overload or the overhead, and the gap reduces to 1 upon n, where n is the number of symbols we group together. So, then we also discussed that instead of doing in a fixed length code, we can use some kind of a variable length code, where we take into account the fact that the symbols do not occur with equal probability. For example, we have taken, if we take the English alphabet, then probably E occurs with highest probability compared to Z, and then we could assign the lowest string length to E and the highest string length to Z, so that overall when we take the average number of bits per symbol, what we get to is lower than what you would use in a fixed length code. And we had taken a particular example in the previous lectures, and we had showed you that it is better to use variable length code. Now, when we did variable length code, what we saw is that if we are not wise enough, then what could happen is that the receiver could get confused as to which particular code was sent. Although the receiver has a code book which is shared with the transmitter, but still the receiver may get confused. For example, if I have 3 symbols A, B and C, and I use 0 for A, 1 for B and 0, 1 for C, in that case when a 0, 1 comes, the decoder does not know whether it is a or a B or a C. So, whereas there was another example which was taken, and A was given the code, let us say 0, B was given 1 0 and C was given 1 1. In that particular case, we found that each of the code were in such a manner that the receiver could parse it in such a way that it would not cause any confusion. So, what we are hinting towards is that we get something known as unique decodability condition. Unique decodability condition, what we said is that when the bits come in, assuming there is an initial synchronization, it will read every bit, go into the code book and check if that particular bit is in the code book. If it is not in the code book, it comes back and records the next bit, and now these 2 bits become a code word. It goes back to the code book, checks if that code book, if that entry exists in the code book, then it decodes the symbol. If it does not exist, it releases it. If it exists, then it records that particular entry as the symbol that has been sent and clears the buffer. It starts reading or parsing for a new code word from the next bit onwards. So, in that manner, it can decode every symbol almost instantaneously. So, also what we will see is these type of codes are also known as instantaneous codes, and what we assigned what we came up to was the term known as prefix free code. What it meant is that every symbol, when it maps to a particular code, is unique, and not only that, it will never be a prefix of any other code. It can be a unique, but if it is a prefix, then it does not serve the purpose. For example, if I take a 1 0 as one of my codes and another code is 1 0 1, in that case, since 1 0 is a prefix of 1 0 1, while decoding, the moment the receiver finds 1 0, it will decode it as the previous symbol compared to the other symbol. So, what we landed up into was the definition of prefix free code. So, when we discussed prefix free code, we said that you can construct a binary tree which grows from the left and goes towards the right, and it starts at the node, and at every node that we generate in the binary tree would either be a code which is a leaf node, or if it is an intermediate node, it will be a prefix of some other code, and only the leaf nodes will be assigned as code words, because the leaf nodes would be unique. And we have also taken one example where we had seen it is the binary code starts from here and it grows from the left to the right. So, this could be assigned as 1, this could be assigned as 0, there is an intermediary node and the tree keeps on growing 1 and a 0, and the tree keeps on growing, right. And you could assign this particular leaf node as A, this particular leaf node this particular leaf node as A, this particular leaf node as B, this particular leaf node as C, and then B would get a code word of 1 1, A could get a code word of 0, and C could get a code word of 1 0 1. In this case, what you will find is that this is unique, there is no prefix, but still we have some more things to take care of, and those few definitions which are very important for designing an efficient prefix free code is what we are going to start off with today. So, if we look at prefix free codes, what we can say is that we are going to look at the prefix free condition that we have mentioned in the previous lecture. So, what we will say is that the prefix free condition ensures that each code word corresponds to a leaf node. That is what we have just mentioned, that is, no adjoining branch going to the right. So, that means this is absolutely, these three that we have identified are codes, there is nothing which goes to the right of each one of them. So, absolutely perfect, there is no problem. But we have another interesting point which is very important. A prefix free code will be called full. Now, this is important, will be called full if no code word can be added without destroying the prefix free property. So, this is one part. So, that means I cannot add another code word. If I can add another code word to this without destroying the prefix free property, that means this is not full. So, we will see something more, and I will write in short, a prefix free code is also called full if no code word can be shortened without destroying the prefix free property. Right. So, if we look at these two, the first thing that we have here, that a prefix free code will be called full if no code word can be added without destroying the prefix free property. Now, if we look at this tree, we can easily add one more branch over here without destroying the property, right, but we cannot add anything here because then B will become a prefix. Okay. And if we look at the previous definitions, previous steps in the definition, what we said is any node that you see, the nodes that you see over here, these nodes are either intermediate nodes, that means they are prefix, or they are leaf nodes, that means they are code words. So, now in this case I can add one branch to this and it does not destroy the prefix yet. So, if I call it something, its name will be 100. So, this will be 100, let us say I put it as D, right. So, this is not a prefix of anything and hence it can easily be added without destroying the prefix free. So, that would clearly mean that this is not a full tree. The second definition, the second statement here has a prefix free code is also called full if no code word can be shortened without destroying the prefix free property. Now, you should always note that this is a prefix free code, there is no problem with it, but if I redraw it and I say that this is part, right, and I have this as leaf nodes, I call this A, I call this B, I call this C. So, in other words, I have shortened this code, I have removed this particular branch. This is also feasible. So, if I do that, I get 1 0. So, this is how I get. So, A remains 0, B remains 1 1 and C becomes 1 0. So, if we compare these two, what we get, A is as it is, B is as it is, only C is 1 0, one of the 1 is dropped. So, that means C is shortened from a 1 0 1 to a 1 0 without destroying the prefix free property, right. So, this is very important to note. So, this particular tree we can call a full prefix tree, a full tree, right. So, this is an example of a full tree and this is, you can say, a non full tree and not a full tree, right. So, both are prefix free, there is no problem with this. If I now apply these two to this tree, what we get is that I cannot add anything. So, if I look at this, if I add, I will be growing the tree further, right. So, it says you cannot add to the existing tree. If the tree was here, we could say that yes, this is something which I could have added, while if I add this, I am not destroying the prefix free property, but still I am able to remain within the tree structure. But here what is happening is I have if I have to add a tree, I am changing the tree. This will be a different tree if I add it into this. And if I shorten C, suppose I short this tree, I want to make it 1 instead of C as 1 0, I want to make it as 1. So, when I make it 1, it is an intermediary node and every intermediary node is a prefix. So, this point, this is a prefix, only leaf nodes. So, that means I cannot add this condition and this condition I cannot shorten. So, B if I shorten, it becomes an intermediary node, C if I shorten, it becomes an intermediary node. So, if I do any of these things, then it does not the prefix free property does not hold, and then I can say that the tree is full. Now, this is very important. Now, what is the importance of a full tree is what we are going to see very shortly, because the importance that you see, if it is not a full tree, the important thing to note is that I can add a code to it. So, that means the code is somewhat not efficient, you can say, or in some manner, I mean, it is not quite correct to say it is not efficient. You can say that there is some provision to take a few more symbols. And if you can shorten, that means we have been unnecessarily using a longer code length, right. So, which we do not want to do, because if I am using a longer code word which is not necessary, then I am basically unnecessarily creating more bits, which is going to penalize my bandwidth, that means going to use up extra bits per second or extra capacity of my communication link. So, I would like to have it as less as possible. So, full tree is very important. So, in this context, we move forward and we have something known as the Kraft inequality. So, Kraft inequality is something which tells us that whether it is possible to construct a prefix free code with a set of code word lengths. For example, I give you a set of code word lengths, let us say 1, 2, 2. So, that means there will be one code word with a length of 1 bit and there will be 2 code words with lengths 2 bits each. So, now the question is, I have not given you code words, I have given you lengths. Now, what we should understand is that lengths are very important for us. Once you have the lengths, then you can construct prefix free codes. Now, this connection is very important, because if you start constructing the code, one can approach that, but rather it is quite interesting that what would be my average code word length. Now, this is because this finally decides the bit rate of the source. So, Kraft inequality is something which will tell you that given a set of lengths, whether prefix free codes are possible or not. This is something critical. So, we can write down that it is a condition determining whether it is possible to construct a prefix free code for a given discrete source alphabet X with symbols, let us say A1, A2, AM. Now, it is not important what we put, we just put that there are AM alphabets with a given set of code word lengths marked by L of AJ, where J is less than or equal to M starting from 1. So, this, if you note the way we are changing from the initial few statements, what we are saying is that let there be a discrete source with this alphabet, that means X defined by this set of symbols. So, which goes with our previous example, you can take the die this is one example. You can take the heads and tails of a coin. You can also take letters of English alphabet, as we have been always saying. So, if we say that this alphabet is given, and now we say instead of probabilities, what we are talking about is, suppose a few lengths are given. This is important. We are not talking about the code, we are saying code word lengths. We have not said about the code word, only the lengths. Now, given these lengths, code word could be any combination, that is a different story. So, now given these lengths, whether from these lengths you can construct codes. Look at the construct. I have given you a symbol and a set of symbols, which is an alphabet. Now, with these symbols, I have also given you a few set of lengths. So, as if there is a set of symbols A1, A2 up to, let us say, AM, and I have told you that let there be certain lengths. So, which maps L of A1 and let us say this is length of AM. So, let there be 1:1 mapping, okay. And there could be 1 to many mapping also, does not matter. That means a few code words have the same lengths, not a problem. We have not talked about code words itself, this is important. So, all we want to know is that if it is possible to construct a code word which is prefix free. Now, once you know that it is possible to construct a prefix free code, then life is easy. What you can do is you can refer back to this binary tree and you can construct the code tree, and then you can assign the leaf nodes, and you know from our previous discussion that this tree forms a prefix free code, right. So, at this point we have this theorem or known as the Kraft inequality. So, it is also known as theorem for Kraft inequality for prefix free code. So, it states that every prefix free code for an alphabet, let us say x, which is equal to A1, A2 up to AM, with code word lengths L of AJ with J ranging from 1 to M satisfies this inequality. Sum of j equals 1 to M 2 to the power of minus L of AJ is less than or equal to 1. So, if I give you, let us say, the lengths as 1, 2 and 2 and ask you that whether I can construct a prefix free code with this or not, what you are going to do is 2 to the power of minus 1 plus 2 to the power of minus 2 plus 2 to the power of minus 2. So, that means a half plus 1 upon 4 plus 1 upon 4, which is equal to half plus half, that is 1. So, that means this sum, which is the left hand side, is less than or equal to 1. So, if since it is equal to 1, then we can say that yes, this inequality is satisfied, which means that a prefix free code can be constructed. Now, what is the importance of this? The importance of this is that since I know a prefix free code can be constructed, I can easily go ahead and construct the prefix free code. Now, how do you construct the prefix free code? Get back to the tree and construct this tree, which has code word length of 1. So, length of, if I call this A, is equal to 1. I can call this as B and this is 1 1. So, length of the code word for B is 2 and this is C, and I can say length of C is 2. So, clearly A is not a prefix of B or C, and it is a full tree that I have constructed, and from this example you can also see that this, if the tree is full, this inequality is satisfied with the equality constraint. Now, if it is not a full tree, then that you can easily guess that it will be less than 1, this will not be equal to 1. So, that is another criteria or another condition through which you can check whether the tree that you are going to construct will be a full tree or will it not be a full tree. The advantage of full tree is that you are using the full set of symbols as best as possible. So, we carry on with this, and you can additionally say is that conversely, if this summation that j equals 1 to capital M 2 to the power of minus the lengths of the code words are less than or equal to 1, that means if this inequality is satisfied, then a prefix free code with length of AJ 1 less than or equal to J is less than or equal to M exists. Moreover, every full, this we have already said, prefix free code satisfied if I say this is, let us say, A, this is A with strict equality, right. So, what we mean by this is that you have this set of symbols. These symbols you are mapping to binary sequence. So, what we are asking the question, before we map to that binary sequence, whether at all prefix free codes can be formed with a certain set of lengths, right. And then you go ahead, once you know that yes, a prefix free code can be constructed, then you form the tree, and once you form the tree with appropriate lengths as you need, then you can easily choose the code words as the length or the leaf nodes, and you can construct the tree. So, now a proof of this is there is a logical proof for this particular statement, and there are many ways to go around this particular proof. So, one particular way of doing it is, you can consider a binary string. This is a decimal point. So, as this can be expressed as the real number. This binary string can be expressed as m equals to 1 to, let us say, L y of m 2 to the power of minus m. So, that means if I write a point 1, that I get 1 multiplied by 2 to the power of minus 1. So, half, and this has an interval 2 to the power of minus L. So, if there are L bits in it, the interval is 2 to the power of minus L. So, for example, if you have 0 point, or if you have 0.011, this would map to 0 plus 1 by 4 plus 1 by 8, because this is 0, 1 multiplied by 2 to the power of minus 2 plus 1 multiplied by 2 to the power of minus 3, and this has an interval of 1 upon 8. Now, so that means this particular sequence, it covers an interval which is marked by 2 to the power of y of m, 2 to the power of minus m, m equals to 1 to L, to m equals to 1 to L, y of m 2 to the power of minus m plus 2 to the power of minus L, because this is the interval length which we have set. So, that means this particular one covers this region from this to this plus 1 upon 8. So, this is the interval which it covers. Now, at this point you can note that all the codes that form part of this are unique. So, that means these codes do not overlap, that means there is no prefix when we say it is a prefix free code. So, if they are all unique, that means they do not overlap, because they form different intervals, these different intervals. And if you see the length that it would cover, so it would cover a length from 0 up to 1, right, that is the full length that it can cover, and every length being unique, that means this interval formed by a particular code is different from another interval formed by a code, and if it is a full tree, it is going to cover this full length between 0 and 1, and if it is not a full tree, it is not going to cover this full length from 0 to 1, it will be less than 1. So, that is an intuitive way of describing that you have parts which add up to form a maximum value of 1, or it can form values which is less than 1. Another very simple way of looking at it is could be when the code tree starts, it starts from here, and this is the minimum code tree that you can have. So, these are the code word lengths that gets added, and what we have seen is that when you have such a source, these symbols are probabilistic. Of course, if they come with equal probability, still there is certain amount of probability, but they are probabilistic in nature, and what we will find later on is there is somewhat connectivity of this length with this probability. So, what we see is that in this, a full tree, you can assign it a value of 1 over here, and you can say there are every node it splits into a value of half, right. This is 0, this is 1, and whenever there is a split, these values add up to the value of the node. So, again this will be half and this will be half. So, even if it does not extend, this arm is half, this arm is half, this is split into half of half and half of half. So, that means at this point the value is 1 by 4, at this point the value is 1 by 4. Now, if this one splits further, this is half. So, this half of this value, half of 1 by 4, half of 1 by 4. So, that means this value is equal to 1 by 8, this value is equal to 1 by 8, right. So, again that is also available from here. That means, we are basically doing the same thing in another way. So, at every node you have the same value, and even if it splits, the sum value up to that node remains the same, and the starting point is this is 0 and this is 1. So, there is half and half length assigned to these. So, again if you add this up, it comes to 1. So, what we have over here is it's kind of a more of a logical proof at this point, and what it summarizes to tell us is that if this particular inequality that we have over here, or we used over here, is satisfied by this set of lengths, all it tells you is that you can construct a prefix free code. Prefix free code is very important, which we have established earlier. Now, once you know that a prefix free code can be constructed, you can construct a binary tree with appropriate lengths. Once you construct a binary tree with appropriate lengths, you just assign symbols to the leaf nodes and you get codes corresponding to those code words. So, we stop this particular discussion at this point and we continue on source coding in the next lecture. Thank you.